Have you ever played a first-person shooter like Quake and wondered how your character doesn't just walk straight through walls? It's easy to take for granted the fact that the game world obeys the laws of physics, but how is that done? In this video, we'll take a deep dive into the data structure that Quake uses for collision detection, one of the most revolutionary in computer graphics. So fire up your curiosity and let's explore the hidden mechanics that make Quake and other games like it possible. Before we get onto that though, let's start with a warm-up. Given a point in space, how do we know whether that point is in empty space or is in a solid such as a wall or floor? Quake answers queries like this using a data structure known as a BSP tree. BSP stands for Binary Space Partitioning, and it does just what the name suggests. It recursively splits space into two, represented in memory as a tree. Each internal node of the tree corresponds with a plane in space. The plane splits the remaining volume in two. The plane has a front side and a back side, with the back side being the first child of the tree and the front side the second child. This division continues recursively on each child until each piece is either completely solid or completely empty. To determine whether a given point, here indicated by a crosshair, is in solid or empty space, we walk down the tree and at each node work out whether we're in front of or behind the plane for the node we're currently at. If behind, we go left, and if in front, we go right. When we reach a leaf, we simply read from the node itself what the contents are. Here's Quake's first level represented as a binary tree. As you can see, it's pretty big. It contains 2,428 leaves and at points is 61 steps deep. We can apply the same principle as before to find the contents of a given point. Once again, we navigate the tree walking left anytime we are behind the splitting plane, and walking right when the target is in front. Since the tree has a depth of 61, any contents queries can be answered in less than 61 iterations. The BSP trees were calculated during level development and are distributed with the game as part of the compiled map. The nodes are stored in an array, and each node contains a reference to its splitting plane and the indices of its children in the array. Leaf nodes are not stored directly, but are implied by a negative child index, -1 for empty and -2 for solid. The function to find the contents of a given point, SV whole points contents, navigates this tree, stepping from node to node until a leaf is encountered. It is implemented as a simple loop, first checking the side of the plane that the point is on, before moving on to the appropriate child. The function stops when a leaf is encountered, that is to say, when the node index becomes less than 0. Next, let's look at tracing a line through a level. This is done at many points in Quake, for example when determining where a bullet should impact. The input to the routine is a start point and an end point in space. We wish to find the first point that this line segment enters a solid leaf, if any. Since a BSP tree is a recursive data structure, each child of a node is itself a tree, it seems natural to use a recursive function to solve this problem. So let's start by writing a specification before starting on the implementation. The function takes a node number and a line segment that lies within the node. The function returns a boolean saying whether the line segment intersects a solid. If so, the first point of intersection is also returned. The line segment is defined as a start point P1 and an endpoint P2. The point of intersection is the nearest point to P1 that is both on the line segment and in a solid. We can immediately implement the function for leaves. For solid leaves, the line segment always intersects since the line segment lies within the leaf and it is known to be solid. Since P1 is in the leaf, the nearest point of intersection to P1 is P1 itself. For empty leaves, there is never an intersection since the line segment lies entirely within the leaf, which we know to be empty. If we're in an internal node, there are two easy cases we can handle first. If both the start and end point are on either side of the split, then we can defer to the node that they both lie in. Finally, If the start point lies in a different child to the endpoint, we step through the near child first, followed by the far child if necessary. This code finds the point that the line intersects the split plane. With this midpoint, we can break the original line in two, one half in the first child node and the other in the second child node. We then recursively call the trace function, passing the child node that the start point lies in, along with the corresponding line segment. If we hit something, there is nothing more to do. Otherwise, we continue the trace on the far side. In this example, we trace a line from the bottom into the solid area at the top. Let's step through each recursive call as the trace is performed. Notice that the function encounters only the leaves that intersect the line, and furthermore, the leaves are walked in near to far order. The function stops when a solid leaf is encountered. The code presented here is a sketch version of the real function, SV recursive hull check. The real version is more robust to floating point error, returns a surface normal at the collision point, and is likely more efficient. Still, the essence is the same. I encourage you to read the full version if you're interested in finding out more. Now we know how to trace a point through space. This is great for things like tracing bullets, which are modelled as points, but what about working out when the player should collide with the world? The player entity is modelled as a non-rotating cuboid, or to put it another way, an axially aligned bounding box. Logically then, we need a function for sweeping a box through space, returning the first point that the box intersects with the solid. Quake has a trick up its sleeve to make this exactly as easy as sweeping a point, but before we do this, we must take a step back and look at how levels are created. Quake maps are constructed as a series of convex building blocks known as brushes. BSP, part of Quake's map compilation toolchain, takes this brushwork and constructs a BSP tree so that there are solid leaves in places that are inside brushes and empty leaves everywhere else. Since brushes are convex and the player bounding box is convex, we can use a trick known as the Minkowski difference to expand the brushes in a very particular way. Under this transformation, the player's bounding box will intersect with the original brush whenever a point at the player's origin intersects with the expanded brush. BSP expands the brushes using the Minkowski difference with the player's bounding box and constructs a second BSP tree which is stored in the compiled map. A further tree is computed for a bounding box matching the ogre's dimensions. Whenever a box trace is needed, one of the three collision hulls is selected based on the box size and a line trace is performed with the corresponding collision hull. If this line trace hits anything, then the point of intersection is the first point where the box hits the original hull. BSP trees are used extensively in Quake, and I've barely even scratched the surface. Their power lies in their ability to exactly describe a 3D volume while being hierarchically structured, permitting divide and conquer style efficient algorithms such as the ones described here. While their use may have declined in recent years, BSP trees truly were one of the workhorses driving Quake. If you've made it this far, thank you for watching. Please consider subscribing and let me know what you think in the comments.